Hello friends, today we are going to study about stiffness matrix method of structural analysis. Before going to the understanding of stiffness matrix method, first you should be able to understand what is kinematic indeterminacy. Kinematic indeterminacy is nothing but it is the degree of freedom available at a particular joint. So for example, you have a beam, continuous beam with the, at point A you have a fixed support, at point B you have a hinged support, and at point C you have a hinged support. You can see here at point A, since it is a fixed support, it is not allowed to rotate or not allowed to move any directions. Hence, kinematic indeterminacy at point A is 0. Whereas at point B, it is a hinged support. Kinematic indeterminacy at point B, you have 1, that is theta B. It is free to rotate at point B, hence theta B is the kinematic indeterminacy. Similarly, at point C, it is a hinged support, hence theta C is the kinematic indeterminacy. In order to develop a stiffness matrix for this particular beam, first you need to assume some directions. These directions are assumed based on the kinematic indeterminacy. For example, if you have theta B as the kinematic indeterminacy, the deflector shape usually it will be something like this. Hence theta C comes here, theta B will be like this, okay, and this is theta B, and depending upon these two directions, we are going to assume the directions for stiffness matrix method. Usually for theta we assume rotational directions, and if you have a displacement like delta, we assume force directions. Either it may be left side direction or right side direction or vertical direction or anything like this. Okay, so always the force direction is accompanied by delta, and rotational direction, that is movement, is accompanied by theta. So for theta B, you have the same beam I will draw here. This is point A, this is point B, and this is point C. Okay, for theta B, since you have kinematic indeterminacy is theta B, we assume direction as rotational direction, and we'll name this rotational direction as 1. Similarly, you have at point C, the kinematic indeterminacy is theta C. We assume rotational direction for C, and we name it as second direction. So depending here at point A, you don't have any kinematic indeterminacies, so we don't assume any directions. So depending upon these directions, the stiffness matrix for this particular beam is calculated. Hence, one thing you have to keep in mind, theta is always accompanied by moment direction, and delta is always accompanied by force directions. Next, we go with a problem so that it is easy to understand how to solve using stiffness matrix method. This is the easiest way to solve the problem using stiffness matrix method. So first thing you have to note here is, for a simple beam, for example simple beam AB, here in this particular beam we have assumed one direction, that is direction 1, and this is our second direction. These directions are assumed based on the unknown at A and B. For stiffness matrix method, the unknowns are, one is theta B and theta A. For theta A, that is which comes at this particular point, okay, for theta A we have assumed one direction, that is direction number 1. For theta b, we assume second direction, that is direction number 2. Both these directions we are assumed in clockwise directions. So here, if you want to find the stiffness of this particular beam AB, we already found it. It is K in 2 into 2 matrix. Okay, because we have two unknowns. So when you have two unknowns, your stiffness matrix will be 2 into 2 matrix, which include 4 EI by L, 2 EI by L, 2 EI by L, and 4 EI by L. This you have to remember. And the next part you need to remember is this formula, that is K matrix into delta matrix is equal to P naught minus PL. Usually these two together we call it as force matrix. That is, it is something like this: K matrix into delta matrix comes the force matrix. Okay, based on this when we solve the problem, we will be clearly understanding what is P naught, what is PL. Okay. Here P naught is the external force or external moment which applies at direction 1. Then P naught will be that particular moment. And PL is the internal moment what is developing because of the external force. For time being, we'll stop here. We'll go with the problem, and when we solve the problem, you can clearly understand what is P naught, what is PL. Okay. Before going to the problem, first thing you have to note here is, here delta means it may be theta or it may be delta, or horizontal displacement or the vertical displacement, or it may be a rotational displacement. Okay. For example, if you have a frame like this, okay, here I will assume one direction, that is this direction. This is my first direction. Now whenever I assume a direction that is a force direction, this force is always accompanied by delta. If I, in the direction 2, second direction, if I assume a rotational direction, this direction is always accompanied by theta. This you have to remember. Now we will go with the problem. First, you can see this problem. You have beam A, B, C, for which you have to analyze and draw SFD and BMD. Okay, I think drawing SFD and BMD easily can do, but only thing is you have to find MA, MB, and MC. MC is already equal to 0 since it is a hinged support. So always the first step is calculation of fixed end moment. So when you go with the fixed end moment, MFAB is minus WR square by 12 and it's equal to minus 16, MFBA is 16, MFBC is 70 minus 71.11, and MFCB is 35.55 kilonewton meter. Now we are going with the step 2. Step 1 is common, and I think all of you know how to calculate fixed end moments. Step 2 is very, very important. That is calculation of stiffness matrix. Here first, in order to calculate stiffness, first you need to assume the directions. For that, now I will draw only the beam. This is my beam A, and in the center you have a hinged support. This is B, and in the other end you have point C. Okay. Here my unknowns are, you can clearly note theta A is equal to 0 because this is a fixed support. So there is no unknown at A, because there is no kinematic unknown at A. So I will name this as my 0. There is no unknown. When I am coming to point B, I have one unknown, that is theta B. Okay, so for this purpose I will assume one direction here. Okay, this is my first direction. Similarly, at point C I have one unknown, that is theta C. For this again I will assume one direction, that is my second direction. Now we are going to find the stiffness matrix for the full beam. Before going to find the stiffness matrix for full beam, first you have to find the stiffness matrix for this small span, that is for span AB. So for span AB, the formula remains same. Okay, it is given AB has a value of EI as I, and it is 4 meter. So for kinematic stiffness of member AB is equal to formula is same, it is 4 EI by L, 2 EI by L, 2 EI by L, 4 EI by L. Okay, this is the formula. Here you should note the values you have to consider here for A and B is 0 and 1. So I will write this as 0, 1, 0, 1. Okay, now this is equivalent to 4 EI by L. L is 4 meter, that is span of AB is 4 meter, and the value of EI is I itself. So 4 EI by L, this is 2 EI by L, that is 4. This is 2 EI by 4. This is 4 EI by 4. If I simplify the same thing and I will take EI outside, what I will get is this is 1, half, half and 1. And the values here you can note the values is 0, 1, 0, 1. Now this is the stiffness of member AB with values 0, 1, 0, 1. Similarly, now we are going to develop the stiffness matrix for span BC. Okay, for the span BC also the stiffness matrix remains same, 4 EI by L, 2 EI by L, 2 EI by L, 4 EI by L. Okay, but the only thing you have to remember here is the values here, the naming given here is 1, 2, 1, 2, because for B the numbering is 1, for C the numbering is 2. So the stiffness matrix is 1, 2, 1, 2. And the value is, first value is 4 EI by L. Since EI is constant, you can write it is 4 into EI. Here 4 into EI is 2 EI, because the value of B is 2 EI and it is the distance is 6 meter. So it is 4 into 2 EI by 6. This is 2 into 2 EI by 6. This is 2 into 2 EI by 6, and this is 4 into 2 EI by 6. So altogether KBC is nothing but, I'll take EI outside, okay, and this becomes 1, 2, 1, 2. This is 4 into 8 by 6, or it is 4 by 3. So this is 4 by 3, this is 2 by 3, this is 2 by 3, and this is 4 by 3. So you got the stiffness matrix of AB. This is for stiffness matrix of AB, and this is the stiffness matrix of BC. Now you need to find the combined stiffness matrix of full beam, that is ABC. Okay. Here total unknowns in full beam is only 2, that is theta B and theta C. So your final stiffness matrix will be 2 into 2 matrix. That is 1, 2, 1, 2. This is your final stiffness matrix, 2 into 2. Here the first term is 1 into 1. What you have to do is find 1 into 1 in both the stiffness matrix. Okay. In AB, in stiffness matrix of AB, 1 into 1 is this particular value, that is 1 into EI. Okay. In both cases we have kept EI constant, so here also I will keep EI outside. So this component is 1 into 1. you have 1 into 1 here, that is 1, and 1 into 1 here, that is 4 by 3. So add these two values, 1 into 1 values, 1 plus 4 by 3, you will get it as 7 by 3. Okay. Now similarly, this component is 2 into 1. We don't have 2 into 1 in this particular matrix. You have 2 into 1 only in this matrix, and the value is 2 by 3. So I'll write this as 2 by 3. Here also you have, it is 1 into 2. You don't have 1 into 2 here. You have 1 into 2 only in this particular matrix. So this value is 2 by 3. And the last one is 2 into 2. You don't have 2 into 2 here. We have only 2 into 2 at this particular matrix, that is 4 by 3. So my matrix is 4 by 3. So this is my final stiffness matrix. Okay, so coming to the formula, we have K matrix into delta matrix is equal to P naught minus PL. Okay, here K matrix is already we have written, that is 7 by 3, 2 by 3, 2 by 3, 4 by 3. So I'll write the same thing. K matrix is 7 by 3, 7 by 3, and it is 2 by 3, 2 by 3, 2 by 3, and 4 by 3. This is my stiffness matrix, that is K matrix. Okay, multiplied by this is actually we have 1 2 1 2. Okay, now coming to delta matrix, first value is 1, second value is theta. Okay, here you can see my first value is unknown is theta b, my second value unknown is theta c. So in delta matrix, as I told earlier, delta may be theta or it may be delta depending upon the direction what we assumed. So here the direction, both direction 1 and direction 2 are rotational directions. Hence first comes theta b, and second comes theta c. These two are the unknowns for our case. Okay. This is equivalent to P naught. Okay, this is P naught. Again, P naught for first direction, P naught for second direction. This is my P naught for first direction, P naught for second direction. P naught for first direction is nothing but if there is any external, this is my first point or first direction point is point B. If there is any external moment acting at point B in the same direction as direction number 1, then that value is considered as P naught. For example, in point B, we don't have any external moment acting at B, hence P naught becomes 0. Similarly, in direction 2, that is the direction 2 what we assumed at point C, if there is any external moment acting in the same direction, okay, that is any external moment acting at point C, then that becomes our P naught. Okay. So here in both points, point B and point C, we don't have external moment acting, hence this becomes 0. So it is 0 minus PL. Okay, coming to PL, in PL also this is my first direction, this is my second direction. Okay. My first direction is point B, my second direction is point C. How many fixed end moments are acting at point B, that you have to add and you have to write it there. For example, in point B you have two fixed end moments, MFBA and MFBC. MFBA is MFBA you have 16, so in direction 1 you have plus 16, okay, and that is MFBA, and the second one is MFBC. MFBC we already written, it is minus 71.11, minus 71.11. Okay, so this is in our direction 1. Similarly, we have to go with direction 2. In our direction 2, that is at point C, how many fixed end moments are acting? You have only one fixed end moment, that is MFCB. MFCB is 35.55. We don't have MFC other part. So only one fixed end moment is acting at point C. So that fixed end moment we will write it there. That is 35.55. 35.55. So you have written the equation. Now this is my K matrix. In order to find theta B, theta C, you have to take this part on the other side. So it becomes K inverse. Okay. So K matrix we already written into delta matrix, that is theta B and theta C, is equal to 0 minus of this one. So the value comes to be 16 minus 71.11. It comes to be minus 0 minus of this value. So I'll write it here. It is 0 minus 55.11. Minus 55.11, and the second value is 35.55. So minus of minus, okay, this becomes plus and this becomes minus. So again I will write the same thing. K matrix into delta matrix is equal to minus of minus is plus 55.11 and this is minus 35.55. So minus it plus it become minus, so minus I have written. So in order to find delta, that is K matrix, so delta matrix I'll write K matrix into delta matrix is equal to, okay, force matrix. Now delta matrix, this delta matrix is nothing but is equal to K matrix inverse into force matrix. That is delta matrix is nothing but here I forgot to write EI. Okay, delta matrix is nothing but theta B and theta C. And this particular EI, I'll keep it here itself, that is EIB. EI. Okay, this is equal to K inverse of this particular matrix. Now how to find K inverse? That is very, very important. Here you can, if you have a calculator, it is better. You can easily find the value of K inverse using the calculator. You can see the calculator I have is 991 ms. Here first thing what you have to do is, first you go with selection of mat option, then first you have to input the stiffness matrix K into the calculator. So first shift mat, you have to go with dimensions of you have A, first matrix is A, second matrix is B, third matrix is C. You can select any matrix. You can store 3 matrix in the max. Okay, so first I will go with first matrix, matrix A. So it asks for what is dimensions. You have 2 into 2 matrix, so M is 2 and N is 2. Okay, now it asks for the value of first matrix A11. So A11 we have here is 7 by 3. So I will input 7 divided by 3. Okay, then I will press equal. It will ask for the second matrix. Second matrix is 2 divided by 3, and the third matrix is also 2 by 3, and the fourth matrix is 4 by 3. So now we already stored the matrix in A. Now if you want the inverse of K, what you have to do is shift mat. It will ask for dimension, edit and selection, that is mat 3. So we go with 3. It will ask which matrix you want to select. So we'll go with A, that is matrix A. Just press inverse and press equal to. So inverse of this particular matrix is point. I'll go with another paper. that is K inverse, K matrix inverse is given as K matrix inverse is given as 0.5 is my first value. If I go right hand side, you have minus 0.25. Again, if I go downside, you have 0.875, and if I go with left hand side, you have minus 0.25. This is my K inverse value. This K inverse value I have to multiply with the another matrix, that is plus 55.11 and minus 35.55. So this matrix also you can easily store in the calculator. I'll go with direct calculation. Okay, already it is there. So shift matrix, I'll go with the dimension of second matrix, that is matrix B. Okay, that is selection of the second matrix, that is matrix B. So I'll go with number 2. So it will ask for the m into n. M is 2 here. Okay, number of rows you have 2, and number of column is 1. We already, it is written. Okay, it will ask for first matrix. My first matrix element is minus 55. Sorry, it's not minus, it is plus 55.11, and the second matrix element is minus 35.55. So we already stored now. Now what you can do is direct calculation. You can go shift mat third one, that is first inverse, that is K matrix inverse into your force matrix, so that is matrix B. So shift 4, 3 and 2. So here you can see, if I plus equal to, directly I'll get the answer for EI theta B as 36.44, and EI theta C is on the downside, that is minus 44.88. So you got the answer for EI theta B and EI theta C. Now you can calculate the moments using slope deflection equation. Okay, so use the equation MAB is equal to MFAB plus 2EI by L to 2 theta A plus theta B. Here theta A is 0, you have only theta B, and the answer for theta B is 36.44. You can substitute and you will get the answer for MAB. Similarly, you substitute for MBA, MBC and MCB. You will get all the values of MAB, MBA, MBC and MCB. Okay. Once you get all the values, you can calculate and you can write the, or you can draw the bending moment diagram. Here I already written the values. Okay. Now we will draw the bending moment diagram for this. Drawing the bending moment diagram is again easiest thing you can do. Just remember the direction and draw the bending moment diagram. This is for span AB and this is for span BC. Okay, so for span AB, at point A you have MAB, and MAB is a clockwise movement, so I'll write clockwise movement something like this. Okay, and at BA, MBA is again clockwise. It is something like this, and value is same 52.4425, and the value at A is 2.2215. Bending moment at B is BC, MBC is minus, so it is anti-clockwise, so it is something like this, and the value is 52.4425 because it is minus 52.4425. That is the reason it is acting anti-clockwise, and bending moment at C is 0. So here you can see this arrow is pushing point A towards downside, so here you have to draw the line downside, and the value is 2.2215. At point B, it is pushing the beam, this arrow is pushing point B towards upside, so you should draw the line towards upside, and the value is 52.442. Here also it is pushing the beam towards upside, so we'll draw the line upward. Here it is 0, Now we can join this, you can join this. Now come make this together so that you will get the final bending moment diagram. Okay, you have a point B is here, point A is here, point C is here. Okay, at point A you have one is downside, in point B you have upside, so I'm going to join it. Okay, from this point it is 0 and this value is 52.4425 and this value is 2.2215. Now you need to overlap this with the simply supported bending moment diagram. Okay, simply supported bending moment diagram, you have one is uniformly distributed load, that is 12, so WL square by 12 is you'll get it as WL square by 8 WL square by 8 is 24, so you need to overlap this with 24. It may come somewhere here, this value is 24, so you overlap the simply supported bending moment diagram for and the maximum value is 24 in the center. Similarly, you need to overlap here with simply supported bending moment diagram for BC. For BC, the loading is eccentric loading with 80, so the maximum bending moment will be WAB by L. WAB by L, it is 106, it is 106.667. 106, it may be somewhere here, you need to join. So it is 106.667 WAB by L. So this is my bending moment diagram. We will see the next type of problem in my next video. If you like the video, please like and share. Thank you.